Example 7 here turns out to be extremely easy. All we have to do is multiply the two numbers together to find the answer, but of course we got to read the problem and see that that is the correct application of this multiplication formula for the probability of A and B that we've been talking about. So this shows you an application of using it. So all products on an assembly line must pass two inspections. It's been determined that the probability that the first inspector will miss a defective item is 0.08. So the probability that the first inspector fails to find a defect is 0.08. If a defective item gets past the first inspector, the probability that the second inspector will not detect it is 0.005. Okay? So that's the probability that the second person fails given that the first person failed. Okay? So it's a lot smaller because the first person is catching most of the mistakes. What's the probability that a defective item will not be rejected by either person? Okay? So show you, we really just have to multiply those two numbers together. But why? We want the probability that the first inspector misses and the second inspector misses. Okay? So we're going to multiply them together, and the second one would be a conditional probability. It would be the probability that the first one misses times the probability that the second one misses, given that the first one misses. And I'm saying misses, meaning that a defective item got past them that they didn't detect. And those are exactly the two numbers that we're given. So we multiply together 0.08 times 0.005. You get 0.0004. Okay, so only a 0.04% chance if we converted that to a percent. So extremely unlikely. If the company uses two inspectors, they're going to catch almost all of the defects that come through. Here's another example just to show one more of using the rule. This is actually an independent case. A die is rolled and a coin is tossed. Find the probability of getting a 6 on the die and a head on the coin. This is a case where they're independent. The coin and the die have nothing to do with each other. If I toss a die, that's not going to affect what happens with the coin that I toss. So you multiply the probability of getting a 6 times the probability of getting a head together on those. So these are independent. The probability of a 6 and a head is the probability of a 6 times the probability of a head. Okay? So if these are fair, not loaded dice, you got a 1 out of 6 chance of getting any particular number. And the probability of getting a head we know is 1/2. So we multiply those, you get 1/12. You could write, I didn't add it to the slide, but you could write out the entire sample space. You would have a head and a 1, a head and a 2, all the way down to a head and a 6. So there'd be 6 of them, a head in each of 1 through 6. And there would be a tail in each of 1 through 6. So there would be 12 of them in the sample space. And only one of them would be a 6 and a head. But we can avoid writing all 12 of those by applying the rule here. So let's see what's next. Another card example. If I draw 3 cards, okay, so you can go beyond 2 and you just keep doing the conditional if it's conditional. But if I draw 3 cards from a standard deck, the probability that I draw in this order, I have them numbered, so I mean in this order. The first card's a queen, the second a king, the third an ace. So what's the probability of that? And it's going to be extremely low, right, that that specific thing occurs out of a deck. But what's the probability if they're drawn with replacement and without replacement? That does make a difference. If they're replaced, every time you draw, there's going to be 52 cards, but if you're not replacing them, the number of cards decreases each time. Okay? So part A, you would just multiply together the 3 numbers, and each one's going to be 4 out of 52. If I've got a deck of cards and I draw 1 card, the probability that it's a queen is 4 out of 52. If I put that card back and it's all shuffled up, so I'm drawing a random card again, then the probability I get a king is going to be 4 out of 52. If I put the card back, there's 52 cards in the deck and 4 of them are kings. Same thing with the third one. So if you add a third one on, you just multiply all 3 together. If there's 4 of them, multiply all 4. So we got 4 out of 52 cubed. 4 out of 52 times 4 out of 52 times 4 out of 52, 3 times. Which winds up being 64 out of 140,608, or an extremely small probability of 0.000455. So that's, if you shift over 2 decimal places, that would be about 0.05% if we rounded it off. If you do without replacement, it does change it, okay? The first card, there's 52 in the deck, 4 queens, so the probability that the first card is a queen is 4 out of 52. But if we don't put the card back, there's still 4 kings in the deck if the first card was a queen, but there's only 51 cards left. So the denominators are going to change here. We don't put those 2 cards back. Now there's only 50 cards left, 4 of them are aces. So the probability that we get a queen, king, and an ace if we're not replacing the card is 4 out of 52 times 4 out of 51 times 4 out of 50. which is 64 out of 132,600, or 0.000483. So, in all practical purposes they're almost the same, right? They're matching all the way out to 4 decimal places, but you can see they are slightly different theoretically there. They're not the exact same number if we round to more decimal places. In either case, it's almost 0, right? It's a very slim chance of that happening. Example 10, a coin is tossed 5 times. Find the probability that no heads occur, and part B, that at least one head is obtained. Okay, so the coin toss, one important thing here, it's independent. Every time you toss a coin, it's independent of the previous tosses. Okay? So the probability that no head occurs would be the probability that every single time it's a tail, right? No heads would be 5 tails, tail, 5 times. They're independent, so I would just multiply together the probability that's a tail times the probability that's a tail 5 times. So you would get 1/2 to the 5th, 1/2 times itself 5 times, which is 0.03125. Okay, so about 3% chance. Part B, what's the probability that at least one head is obtained? If you try to do this one directly, there's a lot of possibilities. At least one, it could be 1 head, 2 heads, 3 heads, 4 heads, 5 heads, all the different ways that could happen. You could try to count that up, but it would be really hard. But the key here to doing this one efficiently, at least one head is exactly the opposite of no heads. I can get the answer to part B just by subtracting my answer to part A from 1. Right? No heads and at least one head, they're what we call the complement of each other. They're the opposite of each other in terms of the sets and the probability here. So the probability that at least one head occurs is 1 minus the probability that they're all tails, that no head occurs, which would be 1 minus 0.03125, which comes out to be a very high probability, 0.96875. So about a 97% chance that you get at least one head and only a 3% chance that there's no heads.